A telescope records a pattern that surprised astronomers. 7 streams of light erupting from a single point in space. Not fully random, not entirely chaotic. A pattern that doesn't match typical comet behavior. What would you do if you were the first person to see this? On March 14th, 2025, 3 observatories recorded the same anomaly. An object designated 3I Atlas, an interstellar visitor, already sailing away from our solar system, suddenly revealed something astronomers did not anticipate based on current models. Multiple jets. 7 distinct plumes of gas and dust streaming outward from its nucleus. But it wasn't the number that stopped everyone cold. It was the arrangement. Jets on comets are expected. They're born from ice turning to vapor as sunlight heats a frozen surface. They spray in whatever direction random cracks and fissures allow. Nature rarely produces this kind of symmetry at comet scales. Yet here, in the composite images stacked from hours of observation, was something that looked organized, almost geometric, a rough pattern where chaos was expected. The first researcher who flagged the data thought it was an artifact. Image processing errors happen. Stacking frames from multiple nights can create ghost patterns, optical illusions born from misaligned pixels. But the pattern appeared independently across 3 different facilities, different telescopes, different software, same result. Something appears consistently across independent observations. This is the story of how one object forced us to question what we think we know about the universe beyond our star, and why some of the brightest minds in astronomy are now using a word they rarely allow themselves to say in public: puzzled. Comment what you think is happening, even one word. Traditional comets are violent, chaotic things. When a comet approaches our star, solar radiation bakes its surface. Frozen volatiles, water ice, carbon dioxide, methane transition directly from solid to gas. This process, called sublimation, creates pressure beneath the crust. Eventually, that pressure finds release. A crack opens. A jet erupts. Most comets show 1 to 3 dominant jets, sometimes a weak fourth. The jets point wherever geological happenstance allows. If there's a crack facing toward the warmth, the jet fires sunward. If rotation turns that crack away, the jet shuts off temporarily, then reignites. The positions change. The intensity fluctuates. There's rarely any order to it. 3I Atlas is showing 7 distinct jets. And they're not scattered randomly across the surface like burst pipes in a deteriorating hull. They're arranged in what multiple observers describe as a rough symmetry. Some point directly toward our star. Others aim in nearly opposite directions. A few run almost parallel to each other. 2 appear to form a paired configuration, mirroring each other across what might be the object's rotational axis. This is not typical for most comets. Interstellar objects, visitors from other star systems, typically arrive cold, dormant, exhausted. They've spent millennia in the frozen void between stars. By the time they pass through our neighborhood, most of their volatile ices have been lost or buried beneath radiation process crusts. They should be dead, inactive. 3I Atlas was already defying expectations by showing any jets at all. 7 jets in a structured arrangement pushes this from unusual into scientifically puzzling territory. The orientation problem runs deeper than simple numbers. Jets pointing in multiple directions simultaneously requires explanation. On a slowly rotating comet with a stable axis, you'd expect jets to cluster around the regions most exposed to solar heating, generally the side facing our star. Night side jets can occur if subsurface heat reaches pockets of ice in shadow, but these tend to be weak and sporadic. 3I Atlas shows strong jets pointing in nearly opposite directions at the same time. That demands one of several possibilities. Either the object is rotating in an unusual way, tumbling chaotically rather than spinning smoothly, or its internal structure is fundamentally different from ordinary comets. Or there are multiple source regions across its surface, each responding to heating in ways that shouldn't all be active simultaneously. The rough symmetry observation makes this stranger still. Symmetry usually reflects some underlying structure or repeated processes. Crystals form symmetrical structures because atoms arrange themselves in repeating patterns. Snowflakes grow symmetrical branches because ice molecules bond at specific angles. But comets aren't crystals. They're rubble piles, loose aggregations of rock and ice smashed together over millions of years, barely holding themselves together through weak gravity. How does a rubble pile from another star system produce a symmetrical jet pattern? One hypothesis suggests the pattern isn't real, it's an illusion created by chaotic rotation. If 3I Atlas is tumbling wildly, rotating around multiple axes simultaneously, then different jets might fire at different times as various surface regions spin through sunlight. When you stack images taken over several nights, this time sequence chaos could appear organized, a stroboscopic effect, freeze frames of motion assembled into false pattern. Testing this requires precise measurements of the object's rotation period. So far, those measurements are inconclusive. The light curve, the pattern of brightness changes over time, shows irregular fluctuations that don't fit a simple rotation model. Some observatories report periodic brightness peaks. Others see erratic spikes. The data doesn't agree yet, which raises a question. Are we looking at an object that refuses to behave predictably? Or are we looking at something our models need to be expanded to explain? A equals natural phenomenon. B equals unknown process. C equals something entirely new. Comment A, B, or C. No wrong answers. Brightness variations add another layer to this mystery. When jets erupt, they change how much sunlight an object reflects. More material in space means more surface area scattering light. You'd expect brightness to increase when jets activate. But 3I Atlas shows brightness changes that don't always correlate with jet activity. Sometimes the object brightens when jets appear quiet. Sometimes it dims when multiple jets are clearly firing. Different observatories report different measurements. This could be instrumental error. Different telescopes, different filters, different atmospheric conditions. Or it could mean the jets are affecting the object's appearance in ways that depend on viewing angle. If jets spray material that forms a temporary atmosphere or coma around the nucleus, that envelope might scatter light differently depending on where Earth happens to be in its orbit relative to 3I Atlas. The thermal signature compounds the puzzle. Infrared observations suggest the surface temperature isn't uniform. There are hotspots that don't align perfectly with the regions where jets emerge. Either heat is reaching those areas through some subsurface pathway, or the jets are drawing on reservoirs of ice buried beneath the crust, requiring stored thermal energy we can't directly measure. This is where standard models start to show limitations. The energy source is likely solar, but details of the process are still being refined. If 3I Atlas entered our solar system cold, dormant, essentially dead, where did it suddenly acquire the energy to power 7 simultaneous jets? Solar heating, obviously, but early estimates don't fully match the observed activity yet. The object's distance from our star, its estimated surface area, the sublimation energy required to produce the observed gas output, everything suggests the reaction is more vigorous than simple solar heating models initially predicted. Unless the composition is radically different, standard comets are mostly water ice, frozen H2O, with smaller amounts of carbon dioxide, methane, ammonia, and organic compounds mixed in. Water ice sublimates at specific temperatures. It requires a certain amount of solar energy input to transition from solid to gas. This sets predictable limits on comet activity at different distances from our star. But what if 3I Atlas isn't mostly water ice? Carbon dioxide ice sublimates at lower temperatures than water. If this object formed in a stellar environment richer in carbon compounds, its ice composition could be fundamentally different. CO2-dominated ices can produce more vigorous outgassing with less solar heating. They can also create different fracture patterns in the crust, more linear, more organized, potentially more symmetrical. Organic compounds add complexity. Long-chain carbon molecules can form layered structures as they freeze. If 3I Atlas contains significant organic layers interspersed with crystalline ice deposits, those boundaries might create preferential weakness zones. Cracks would follow layer boundaries. Jets would emerge along geometric patterns defined by ancient freezing processes that occurred in another star system under conditions we've never directly studied. This is the most scientifically conservative explanation for the jet pattern. Different chemistry, different structure, different behavior, natural, but not previously observed in detail. It requires no new physics, just an object that forms somewhere else under rules slightly different from our own solar system's formative conditions. Most researchers consider this explanation plausible because it fits within known physics. Public interpretation moves faster than scientific caution. On social platforms, images of 3I Atlas accumulate commentary that ranges from curious to convinced. Symmetry often draws attention because people associate it with structure. The jet pattern looks organized. If you showed someone a diagram of 7 evenly spaced nozzles on an engine, they wouldn't think twice. This resembles that. Therefore, the logic goes, this must be that. The human brain evolved to recognize patterns. This trait kept our ancestors alive, spotting the outline of a predator in broken shadows, detecting the regularity of tool marks versus natural fractures. We see faces in clouds. We see meaning in noise. We see structure in coincidence. Symmetry triggers that pattern recognition deeply. Nature produces symmetry, but rarely at scales we're discussing. Snowflakes, crystals, biological structures, these are symmetrical because underlying molecular forces dictate specific arrangements. But comet jets, random surface cracks dictated by chaotic impacts and uneven heating, those shouldn't align into patterns. Yet they might. This is the challenge in communicating uncertain science. The honest answer is, we don't know yet. More data is needed, but we don't know sounds unsatisfying. It leaves space for speculation, and speculation fills that space instantly. The scientific community responds carefully. NASA's official statements emphasize natural processes. No evidence of artificial origin. No technological signatures detected. Unusual activity level, yes. Details not yet fully explained, yes. But unusual doesn't mean unprecedented in nature, and unexplained doesn't mean unexplainable. It means we're still working on it. Harvard researchers and independent astronomy teams note the activity level exceeds predictions. They acknowledge the symmetry is rare. They agree this doesn't match standard comet models perfectly. But they also point out that we've only observed a handful of interstellar objects in detail. Our sample size is too small to declare anything truly anomalous. Perhaps we simply haven't seen enough of the universe's variety yet. Does this change how you see our place in the universe? The comparison with Oumuamua is inevitable. That object, the first confirmed interstellar visitor, also behaved strangely. It accelerated slightly as it left our solar system, pushed by some force that couldn't be entirely explained by standard outgassing models. Its elongated shape was unusual. Its rotation was odd. It produced no visible jets, despite showing non-gravitational acceleration. 3I Atlas is different. It's clearly active, jets are visible, dust and gas are definitely present, yet it too shows behavior that doesn't fit neatly into existing categories. Different anomalies, similar outcome. Scientists left with incomplete explanations and open questions. What these two objects share is a reminder of how little we actually know. Every object we study teaches us something new about the diversity of planetary formation processes across the galaxy. Different star systems form under different conditions, different metallicities, different radiation environments, different collision histories. What emerges are objects that challenge the narrow experience base we've built from studying only our own solar system. Sometimes observations fall outside the limits of our current models. Within the next few weeks, several research teams plan follow-up observations. High-resolution spectroscopy to measure exact gas composition. Polarimetry to study dust grain properties. Continued photometry to nail down the rotation period. Infrared monitoring to track thermal evolution as the object moves farther from our star. These measurements might reveal correlations. If the jets pulse periodically, that points toward rotation-driven activity. If gas ratios shift over time, that suggests layered composition with different ices sublimating in sequence. If thermal hotspots align with jet sources, that supports standard sublimation models. If they don't align, we have a deeper mystery. The biggest question remains unanswered. Why is an interstellar object already past its closest approach to our star and heading back into deep space, still producing 7 distinct jets in an organized pattern? Ordinary comets calm down as they move away from the warmth. Activity decreases, jets fade, the object returns to dormancy. 3I Atlas should be quieting. Instead, it continues to perform. Either this object is genuinely different in composition or structure, or our understanding of outgassing physics under interstellar conditions is incomplete. Or we're witnessing a unique moment, a specific configuration of distance, temperature, rotation, and viewing angle that creates an appearance we've simply never seen before. Write one sentence. This means there's a philosophical weight to objects like this. They arrive from somewhere else. They carry physical evidence of alien environments, not alien life, alien physics, applied over billions of years in places we'll never visit. Every measurement we take is a message from beyond. Every anomaly is a hint that the universe contains more variety than our theories predict. We built our science on what we could see from one planet, orbiting one star, in one small region of one galaxy. For centuries, that was enough. Our models worked. Predictions matched observations. We felt confident. Then we developed the technology to spot these visitors. And suddenly, our models strain. Not because they're wrong, but because they're incomplete. They were built on local data, local examples, local experience. Expanding the data set reveals gaps. The symmetry in 3I Atlas's jet pattern might be nothing, a coincidental alignment of unrelated fractures, a temporary illusion created by rotation and viewing angle. In a few months, with more data, this might become a footnote. Just another natural object doing natural things, briefly misunderstood. Or it might be the moment we realize that comet formation in other stellar environments produces structures we never predicted, that crystalline ice layers form differently under different radiation fields, that objects from metal-rich stars carry frozen chemistry that behaves in ways our water ice models never anticipated. Either way, we learn. Either way, the universe is larger and stranger than it was before we looked. The future is uncertain. 3. iAtlas will continue its journey outward. Within a year, it will be too faint for most telescopes to track. The data we're gathering now represents our only chance to study this object in detail. What we learn depends on how quickly observatories can schedule time, how weather cooperates, how funding flows, to analysis teams working long hours on data that might yield no clear answers. Space agencies watch, not because they expect anything extraordinary, but because every anomaly teaches us something. Every object that doesn't fit the model helps us build better models. This is how science actually works, not in sudden revelations, but in gradual refinement, observations that challenge assumptions, measurements that force revisions, patience rewarded with understanding. Eventually, maybe 3I Atlas is unique, a 1 in a million object whose specific formation history created properties we'll never see again. Maybe it's representative of a class of interstellar visitors we simply haven't encountered enough to recognize yet. Maybe it's teaching us that comet physics is more complex, more varied, more sensitive to initial conditions than we thought. The honest truth is, we don't know yet. The data is still arriving. The analysis is still ongoing. The theories are still forming. In a year, this might be resolved completely, or it might join a list of cosmic puzzles we revisit every time better instruments become available. What we know for certain is this: 7 jets, arranged in rough symmetry, erupting from an object that came from somewhere else. An arrangement that wasn't predicted. A pattern where chaos was expected. A visitor that refuses to behave according to local rules. So tell me, what do you think happens next? Maybe the universe has more variety than our current understanding captures.